Welcome back to class time. It's time for CSEC Mathematics. I'm Brittany Henderson.
And I am Wadian Price.
We'll be guiding you through today's lesson on graphing and linear functions.
But before we get started, let us look at our objectives.
All right, so our objectives today is firstly, we're going to be looking at graphing linear functions, determining the intercepts of the graph of the linear functions. So we have two main objectives today: drawing graphs of linear functions, determining the intercepts of the graph of linear functions.
Definitely.
All right, so let's look at this scenario. Linda was having trouble in her math class. So she had some difficulties with the linear functions. So she asked her friend Richard to help her out with these functions, help her to understand, right? So let's see what Richard went ahead and did.
All right, so since Linda has a vending machine at her school, I'll use that example to bring out the concept of a function. So a function functions or behaves similarly to a machine in that it takes an input and it brings out one particular output. So for example, here we'll insert in the machine some money, right? We are expecting to get an output of some form of product. Now, let us say, for example, I input $100 in this vending machine. I am expected to get an output of a potato chips. If I input $150, I am expected to get a banana chips. Similarly, if I input $120, I am expected to get a chocolate. So here we see that one particular output value will give, input value rather, will give me one output. So a function behaves in this manner. It is that type of construct that will take one particular value, push it out, and give you one particular output value. Now, this relationship can be displayed in a table. So here we see in the table our input, $100, and our output, potato chips. Input, $150, output, banana chips. Input, $120, output, a chocolate. Here we have to note carefully that the output gives just one, the input rather gives just one and only one output value. If it gives more than one output, it will not be a function. And as you would have learned in other classes, that there are other relations which are not necessarily a function. So you have the one-to-many, you have the many-to-one, you have the many-to-many. But those are not functions. It has to be a one-to-one for it to be classified as a function. Now, we can move from the table form and write the input and output in ordered pairs. So this is how our ordered pair would look. 100, that is the $100, and the potato chips. Similarly, $150, banana chips. $120, chocolate. Then, as you would have learned as well, that the first value there represents your x value, and the second one represents your f of x. You would have been acquainted with y, x and y, right? And we are going to explain further why we have f of x and not y. Similarly, our $150 would be our x value, and the banana chips will be our f of x. $120, x, and our chocolate will be your f of x. So this is how you would move from your table form to writing this in ordered pairs.
Okay, so now we know that you should be familiar with the Cartesian plane. And as you can see, we have our x-axis and our y-axis. And here we have one ordered pair. So we have a point on our Cartesian plane. And this is 4, 3. So our x component is 4 and our y component is 3. Right? So the point at which both x and y intersect would be our point 4, 3 on our Cartesian plane. Now, what is a linear function? Linear functions are those whose graph is really a straight line. Yeah. So a linear function looks very similar to the equation of a straight line, right? So y equal mx plus c, where m is our gradient, c is our y-intercept. It's the same thing when we're looking at function notation, where we use fx is equal to mx plus c.
Definitely. And we should also note that f of x does not mean f times.
Does not.
Right? So I know students are familiar with when you don't see a sign between two letters, let us say, you know that you're going to multiply. But in this case, f of x does not mean f times x. It is just showing that there's a particular function that is being carried out on x.
Yes. All right, so here we have a linear function. And as was stated before, we can identify our y-intercept at 0, 1. And we can also identify our slope or our gradient, yes. Right? So here our run is 2 and our rise is 1, right? You see that?
Definitely. And this slope, I don't know, Brittany, have you ever traveled on the North-South Highway?
I believe I have. Yes, yes.
What do you think about those hills?
It looks a little bit similar, don't it?
It looks similar.
It looks similar to what I would be traveling on the North-South.
Right.
True.
But there's something interesting about how they display the slope or the grade of those hills, right? And if you look at the signs when you're about to ascend on those hills, you'll realize that they are given in terms of percent.
I've never realized that before.
Yeah.
That's interesting.
Interesting. So
yeah.
It is not in terms, so persons would think that it will be given in terms of degrees, but it is actually given in terms of percent. So for example, if the grade of the hill is 6%, what does that really mean?
I don't know.
Right? No, we cannot. How do we write 6%? How else can we write 6%?
6 of 100?
6 over 100.
Yeah, 6 over 100.
No, it is really saying that the elevation of the hill changes 6 feet for every 100 feet.
Look at that. Math in real life.
Math in real life.
Look at that.
Math in real life.
Look at that. All right, so here we have two linear functions now. So one function is f of x equals x, so our first linear function, f of x is equal to x, and our second linear function is f of x is equal to half x. Now, what do you notice here changing, Mr. Price? What's the difference between these two lines?
Well, I'm seeing that the gradients are different. The gradient, one of the gradients is 1/2, while the other is just 1.
Okay.
The one with the gradient of 1 is obviously steeper than the one with 1/2. So we see how the gradient changes, or the steepness of the line changes as the gradient changes.
Yes. All right, so now we have different types of gradients. So we spoke about the steepness of the line and how the gradients change as the line changes. Now, let us look at our first line, or first function. The gradient here is positive, right? You realize that?
Yes.
For our second function, the gradient is now negative. And for our third function, we have no gradient. What do you notice about this line with no gradient?
Yeah, it's just constant.
It's constant.
Just a horizontal line.
So we're not going up and we're not coming down. It's just going straight across. So it's constant. And then we have a gradient that is undefined.
Yeah.
So these are our 4 main types of gradients. You can have a positive gradient, a negative gradient, a constant gradient, or a gradient that is 0, and we can also have a gradient that is undefined. Now, we talked about applying this to real life when we talked about going on the North-South Highway. Now, let's look at another example. During the past cold front, the temperature of a room was 3 degrees Celsius more than the temperature outside of the room. The temperatures outside went as low as -4 degrees Celsius and as high as 4 degrees Celsius. Richard was asked to plot a graph to represent this information, the information that he went ahead and collected, right? So let's look at the information that Richard collected. So he had his thermometer, he took the temperature of the room on the inside and went ahead and took the temperature of the room on the outside. So here we have the data that he received. So it was -4 degrees Celsius on the outside of the room and 1 degree Celsius on -1 degree Celsius on the inside of the room. Now it seems like Richard is either in a very cold country or way up in the hills, maybe Blue Mountain?
Yeah, maybe.
Maybe. All right. So let us see how he went ahead and displayed this on a graph. Okay, so Richard also discovered that the temperature inside the room was dependent on the temperature outside of the room. He then came up with a rule that allowed him to create an equation for a line before he started to plot his graph. So the temperature inside the room is equal to the temperature outside of the room plus 3 degrees Celsius.
Wow.
It's interesting. Now, this formula looked just like the general form of a straight line. So remember, we spoke about the straight line that you're familiar with. Y is equal to mx plus c.
Yes. And another concept that is coming out here, it made mention that the temperature inside the room was dependent on the temperature outside the room. So here we are having two other words we need to look at, dependent and independent. Which we are going to touch on as we venture further.
So he then found that the specific function for the temperatures recorded were f of x is equal to x plus 3. Richard then gathered his graph paper, ruler, pencil, and went about drawing his straight line graph. In his case, the temperature outside would be the x values,
Yes.
and as we would say, we talked about domain values, and we said independent or dependent. Which one is it, sir?
Independent.
It's the independent variable. And the temperature inside the room is our y values or our range, and those would be our dependent values. So here it is that we have our Cartesian plane. We have our x-axis, which would represent all of our independent values, and our y-axis or f of x axis, which would represent all of our dependent values. So we're looking at the temperature inside and the temperature outside of a room. And we said that the temperature inside and the temperature outside are dependent on each other, right? There's some relationship there.
Yeah.
All right.
All right, so here it is now. So he then went about plotting the points. Now, as was mentioned before, students have to ensure that when they are plotting their graphs, that they use a pencil and not a pen, right? Because we are prone to make mistakes when we are plotting the graphs. So it is always recommended that you use a pencil rather than a pen to plot your graph. Now, he located the value on the x-axis and corresponding f of x values. Now, again, this is important. Your x-coordinate is always before your y. As we have seen in our ordered period before, the first value is your x, the second one is your y. So he located those. As highlighted in the table below, he located -4 on the x-axis first, then -1 on the f of x axis. Now, we may ask, how did he arrive at the temperature inside the room? We know that the restraint was already given in terms of the temperature outside the room. It was between or from -4 to +4. But we also came up with the function, right? Which function did he come up with again?
F of x is equal to x plus 3.
X plus 3. So here we are carrying out a function on x, right? Now, our first x value was what?
Negative 4
Negative
degrees.
4. So when x is negative 4, we're just going to substitute this in the function. So that will be negative 4 plus
Negative
plus
4 plus
3.
3.
And that will give us what?
Negative 1.
Negative 1. So that is our first ordered pair. So when x is negative 4, then y is negative 1. All right? We can try, we're going to try two more. We're going to do the one with 0 and then a positive value. So when x is 0, so that is f, finding f of 0 now. So it is just what? 0 plus 3, which give us 3. Right? So that is how he arrived at those points. Now let us try a positive value. So let us say when
x is 3.
When x is 3. So this would be now x of 3 is equal to 3 plus 3. And that will give us 6. So in this case, our ordered pair would be 0 to 3. In this one, it was what? Negative 4 to?
Negative 1.
Negative 1.
And
right,
the last one is 0 to is 3 to 6.
3 to 3. 3 to 6.
And the middle one is 0 to 3.
This one is 0 to 3.
Yes.
All right? So that's how he arrived at the ordered pairs. So he went about now plotting those points. So here we have the ordered pairs in a table form. So again, those top values, those are your x values, and the ones below that are your f of x. So we're taking the first pair, which is negative 4 and negative 1. So this is where the location of that point is. So as was depicted before, we would first locate our negative 4, and that is on our x-axis, which is our horizontal axis, while our f of x axis, or your y-axis, as you would be more familiar with, would be your vertical axis. But we locate our x value first, and then we find our negative 1 on our y value, and that will be the location of our first point, which is negative 4 to negative 1. Now he continued, and if you realize now, he has more points. So all he did was to plot the other points. And it is important for us to highlight why he plot the points, because now we are looking at a linear function. And a linear function, remember, a linear comes from the word line. So he's actually going to plot a line now. And as we know that a line is just an array of points that extend infinitely in both directions. So now that he has some points, we can now go ahead and draw our line. So here is a line. And again, it is important for us to note that we must label our line. So now the line is f of x equals x plus 3.
All right, so now that Richard is finished, he needs to compare the temperatures inside and outside of the room. He's particularly interested when the temperatures are at 0 degrees inside and 0 degrees outside the room. Richard used the graph of functions to locate 0 degrees inside the room and 0 degrees outside of the room. So let's go back to our graph. Now we need to locate 0 degrees inside our room and 0 degrees outside of our room. Now, 0 degrees inside the room, as you can see, it is where our line cuts the x-axis. So at this point, negative 3, 0 would be 0 degrees inside the room. And we're now going to locate 0 degrees outside the room, and that is going to be 0, 3, which is where our line cuts our y-axis. So if you notice now, 0 degrees inside of our room and 0 degrees outside of our room is actually our x and y intercept. Now this word intercept, I'm sure you've come across it before, and all it simply means is as it says, intercept is where something meets or cuts each other. So at that particular point is where we will find 0 degrees inside and out, or x and our y intercept. All right, so it was at that point that Richard made the link with the intercepts, as we just did, and he found out that the y-intercept is the y value where the function crosses the y-axis, and the x-intercept is the x value where the line crosses our x-axis.
All right, so it should also be noted that at your x-intercept, your y value is 0. And at your y-intercept,
my x value is 0.
0.
All right, so I hope that you guys have been keeping up with us, and let's try one at home. So I want for you to work with me, so I hope you can get out your graph paper, your pens, your pencil, your ruler, and let's work through this one. So a pool cleaning service drained a pool, and the following table gives us the number of hours it took to drain the pool and the amount of water remaining in the pool at a particular time. So if we notice in our table, we have time in hours and the water remaining in gallons. Now, Mr. Price, we talked about some very important things before. We talked about the independent and the dependent variable, don't it?
Yeah.
No, I want for you to help me out, because and help our viewers at home. We need to first identify our independent and our dependent variables, right?
Yeah.
All right, so I'm giving you a moment at home to identify your independent and dependent variables. All right, Mr. Price.
Yes.
So tell me, sir, which one is my independent and which one is my dependent variable?
All right, so if I should reason through this logically, I would see that as time changes, the amount of water in the pool would get less. So the amount of water in the pool is dependent on the elapse of time. So the time here would be my independent variable, while the water in the pool would be my dependent. So the water is dependent on the amount of time that has elapsed.
Okay, so viewers at home, you think Mr. Price is right? Let's find out. So let's look at our graph, and indeed, you're correct.
Yeah.
So our independent variable is time in hours, and our dependent variable is the water remaining in gallons. So as time elapses, it's the amount of water remaining as time elapses. So you're now asked to plot the points that show the relationship between the number of hours elapsed and the number of gallons of water left in the pool. Select a place on the grid to plot each point. No, Mr. Price, I know you feel like I'm picking on you this morning, but no.
You are.
What do you notice about the scale for this particular graph?
Well, on the x-axis, the scale looks fairly normal, right? It runs from 0 to 14. But on your y-axis, the f of x axis, I'm seeing where we start at 7,200, then it goes up to 8,000. However, what I'm seeing is that the 7,200 is not at the 0 mark. Can you explain why?
You know, I was going to ask you that. Why is it that it's not at the 0 mark?
Yeah.
Okay, so it's not that the pool, the gallons of water that we're measuring did not start at 0. But what we actually did here is we just broke our graph a little, and we started off at 7,200.
Okay, fair enough.
All right, so magic. We've plotted our points and we have drawn our straight line. So each one of the points, remember we had our table from before, which showed the relationship between the time in hours and the gallons of water that we had. And what we did was we went ahead and we plotted our points on our Cartesian plane. So as you can see, at 4 hours, we had more than 12,800 gallons of water already out of our pool, right? And Mr. Price, you noticing anything with this graph? Is it looking any way to you? You know, is the graph going up or down? What you think is happening with the slope there, sir?
Well, since the question indicates that we are actually draining a pool, right? So the graph will actually be going down. So when after an hour, for example, the pool would almost be filled 3/4 or fourth. But after 11 hours, the water would be less in the pool. So definitely the graph is going down.
Okay. And you guys at home, you remember that we looked at the different types of graphs? I hope you're bearing that in mind. It's going to come up a little bit later. Now, part B of the question says, the data suggests a linear relationship between the number of hours the pool has been draining and the number of gallons of water remaining in the pool. What does the rate of change represent in the context of this relationship? Now, we have a little thing, a new term here, rate of change. What is that? Mr. Price, you know what rate of change is?
It's the same thing that we have been discussing in terms of the slope or the gradient.
That is correct. So our rate of change is really, we're really looking at the gradient of this line.
Yeah.
Okay. All right. So we have 4 options. You ready?
Yes.
All right. So part A says the number of gallons of water in the pool after 1 hour. The number of, part B, the number of hours it took to drain 1 gallon of water. Part C says the number of gallons drained each hour. And part D says the number of gallons of water in the pool when it's full. Which one of these relationships tells me about the gradient, Mr. Price?
But since we're making reference to rate of change,
Yes.
then we're looking at, as time changes, how the water level changes. So I would say my answer is C.
Your answer is C.
Yeah.
Viewers at home, what's your answer? Ready? All right, let's see. All right, so you are indeed correct. It is C. So the number of gallons drained each hour represents the rate of change in this particular context.
Yes.
Awesome job, Mr. Price. You're on a roll. You're going
Thank
though.
you.
Yes, man. All right. So part C now says, part C says, what does the y-intercept of the linear function represent in the context of this relationship? Now, guys, remember we looked at the temperature inside and outside of a room. We looked at where, you know, our linear function cuts our x and y axis, right? So bear those things in mind. In this particular case, we want to find out what the relationship is with the y-intercept. Now, you want to start off, let's look at the graph. So we have the graph here, and we're looking for the y-intercept. Mr. Price,
Yes.
y-intercept. What am I looking for, sir?
Are you asking me why the intercept?
No, sir, not
Oh,
y the intercept.
The
Yes.
y-intercept.
Yes, sir.
All right, so as we had discussed before, that the y-intercept would be where the graph cuts or meet the y-axis.
All right. So, guys at home, where do you see our linear function cutting the y-axis here? You see it, Mr. Price?
I'm seeing it.
All right, let's go back to our options now. So these are our 4 options. The number of gallons of water in the pool after 1 hour, that's A. B, the number of hours it took to drain 1 gallon of water. C, the number of gallons drained each hour. And D, the number of gallons of water in the pool when it's full. Mr. Price, picking on you today.
Again.
Again, yes, man. So what's the answer?
All right, so let us look back at our graph. So we can see our y-intercept right there. Can you point to it for me, please?
Okay, so our y-intercept?
That's right there.
Right here.
Right? So if we are draining the pool, at that time, if you should move your finger down, right down to, no, down, vertically down, right? It goes right down to 0 hours. So at 0 hours, it simply means that we haven't started draining the pool as yet. So the pool would be at its maximum. So it simply means that at my y-intercept there, the pool would be full.
Okay. So I think you're right, you know. Awesome.
Right, so I think my answer is D.
Yes, your answer should be D. You're on a roll today, though. No,
Yeah.
no thumbs up for you. So you're on a roll. The answer is indeed D. Now, our very last question, or part D, says, which equation describes the relationship between the time elapsed and the number of gallons of water remaining in the pool? Now remember, when we started off, we spoke a lot about the correlation between the line, the equation of a straight line, and the equation that represents a function. Do you remember that, sir?
Yes, we did.
Okay. So we're going to use all the information that we've gathered. Remember the very important parts of the straight line equation. One being the
Gradient.
gradient. Two,
Y-intercept.
and the y-intercept.
Yeah.
So there are two main things that we need to find out. The gradient of this particular function and or y-intercept. So let's see if we can find that out from our graph. You think we can?
We can.
All right, let's look. So going back to our graph, we need to identify the gradient and the y-intercept.
Yeah.
Now, just looking at the graph, our y-intercept is, again, Mr. Price?
That's about 15,000.
So it's about 15,000 gallons, right? So our y-intercept is once again where our function cuts the y-axis. So you can write that down for me, Mr. Price.
Okay.
So my y-intercept in this case is 15,000.
And that is 15,000.
Okay. And we also need to identify another very important thing, and that is our gradient. So going back to the graph, we now need to ascertain our gradient of this particular function. Now, guys, I know that you've looked at gradients before, and you know how to mathematically work out the gradient of this particular line.
Yes.
So what we're going to do, we're going to take 2 points on this line, and we're going to use those 2 points to find the gradient of the line.
Yes.
Right?
All right, so which point
So,
we want to start out with? All right, so let us see, look at our options. So we have already noted that our y-intercept, that is where the graph cuts the y-axis, was at 15,000. All right, so looking at our option, we are using the elimination method. Now, since my y-intercept is that last number that is there in my equation, it simply means that B could never be my answer.
no. And which other one could never be an answer?
C could never be my answer either, because the y-intercept must be 15,000.
Yes.
All right, so I am between A and D.
Okay. So we need to ascertain what the gradient of the time. Let's just do a trial and error and let's see, right?
All right, so
Okay.
let us select a point that was given. So let us say we are selecting 5.
Yes.
5, so we should get what? 12,000?
12,000.
Right, so after 5 hours, the pool was at
12,000 gallons.
gallons. All right, so let us try the first function, which is f of x is equal to
Minus 600x
minus 600x
plus 15,000.
plus 15,000. All right, so we are looking at when x is 5.
5.
So that will be 600 times 5 plus 15,000.
Mr. Price, you're missing something though.
What
Remember,
am I
it's
missing?
negative.
Oh.
Yes, sir.
And that is where students now will make the mistake as well. But why is my gradient negative?
Well, you remember when we looked at the types of gradients, guys, and we had our positive gradient sloping up and our negative gradient sloping down? Now, this particular application is we're draining the water out of the pool.
Yeah.
And remember that our function was actually sloping downwards. So that
Beautiful.
is the reason why the gradient there is negative,
Oh.
sir.
I see. All right, so that's negative. So what negative 600 times 5 will give me? 5 6s?
3,000.
3,000 plus 15,000. And this will give me
12,000.
12,000. Wow.
You know, I think you were, you know, I think you looked at these questions from before because, sir, how you could guess so quickly and
Oh, no,
easily.
when you're bright, you're just bright.
Go on, yeah.
Yeah.
So I hope that you guys at home also got that. So the correct answer in this case is A. So the function is negative 600x plus 15,000.
Definitely.
All right, so just to recap some of the things that we've done today. So we've looked at what is a function, and we have described a function as just being a graph with a straight line, right? The function notation is f of x is equal to mx plus c. We've also looked at the dependent and independent values, my domain and my range values. So my x value is my domain value, while my y value is my range values, or my dependent values. We've also looked at our x and y intercept. Now, the y-intercept is the value of y, where the function crosses my y-axis, while the x-intercept is the value of x, where the line crosses my x-axis. Now, I hope you guys had fun today. That's it for today's lesson. If you have any questions, send them to Television Jamaica's Facebook page at Television Jamaica or Instagram at television_Jamaica, or use the hashtag TVJClassTime. I'll answer as many questions as I can in our next class. Next up, Cape Economics. Stay with us.
Here, interactive classes for all ages on the School Time channel on onespotmedia.com. With a combination of live Zoom classes and recorded class time, Schools Not Out lessons, and numerous educational content, we've created a comprehensive 24-hour channel dedicated exclusively to educating our nation's youth. Early childhood through to primary, secondary, and tertiary, it's one stop on one spot for education 24 hours. Brought to you by the Ministry of Education, Youth and Information in association with Television Jamaica Limited.